Welcome back. This is an Aleks homework video on understanding connections between descriptions of weak acid dissociation. Okay, I think this is an easy problem. I don't think you'll have any trouble with this. They're asking for a pH, which is always a little scary, but really just the pH, you're just going to need to know the molarity of the hydronium ions. If you can do that, you just take the negative log of that and you'll be done. So you don't have to do anything here. You don't need to do an acid constant. You don't have to do an ice table. Really, all they're asking is they're giving you a certain molarity of an acid and telling you after a certain time, which is the equilibrium moment, that you've got 0.054% dissociated. Well, what that means is that you have a weak acid. If all of it dissociates, then you have a strong acid. There's just a few of those strong acids. Here you have an unidentified weak acid, and that weak acid dissociates just a little bit. See, not even a percentage, like 0.5% dissociated. So it just barely is breaking apart. It's very weak. And now from that acid, you're finding out the pH. So I just start with the balanced equation. Now this is the generic equation. You've got HA, the H is representing the proton that's going to be donated in the acid, and then the A is whatever's left over. That's the conjugate base. So you'll see that on the right side, A to the A negative, meaning whatever's left over in that acid. Then that hydrogen, that proton is going to join a water molecule and become a hydronium. That's H3O plus. pH is the measurement of hydronium concentration. So if water dissociates by itself, you're going to get water at like a 10 to the negative 7 concentration, very, very little, and we're going to call that neutral. Anything less than that's going to be acidic. Now it's obvious that if you put an acid in water, it's going to be less than that, and if as long as it's substantially less than that, this is a really easy problem. Okay, so I just find out that after equilibrium, only a little bit of this HA is dissociated. So I simply take whatever the original molarity was, multiply it by 0.054%, which as a decimal is 0.00054, and I get the equilibrium concentration of my acid at 2.214 times 10 to the negative 5. Then I realize that it's a 1-to-1 relationship, that the hydronium is the same number of moles as my weak acid. So if my molar concentration at equilibrium, if I know the acid, then I also know hydronium. Okay, that means that at equilibrium, the hydronium concentration is 2.214 times 10 to the negative 5. So far really easy. Well, it's just easier. You're just going to say, as long as this is substantially less than negative 7, right? So 10 to the negative 5 is less than or greater than 10 to the negative 7, and it's substantially more. So we're talking about the amount of acid. It's way more than just normal. It's way more than just water. Then I can ignore water dissociation and simply take the negative log of this. And so the negative log of 2.214 times 10 to the 5 is 4.6548, whatever. And you're asked to find 2 decimal places. So 2 decimal places is 4.65. So I hope that's helped.